Yeah. Good morning, everyone. Thank you for joining us for the Grasp on Robotics seminar today. I am Pratik Chaudhary. I'm an assistant professor in electrical engineering. I'm filling in for Dinesh Jairaman, who is the official host of our speaker. But he is on a CIS retreat today. So it's not on campus. He's doing something fun. A quick reminder, the recordings of the previous talks are available on YouTube, and you can watch them there. If you're joining from Zoom, please type your question in the Zoom chat, and then we will have it read. We'll read it out during the talk. If you're here in person, of course, just raise your hand and feel free to ask a question. Okay. I would like to introduce, before we begin, our student panelists, Jason Ma, who is a third-year PhD student in computer science. He works with Dinesh Jairaman on robot learning. Aurora Kian, who is a second-year student, third-year student in computer science. She also works with Dinesh Jairaman on more computer vision and representation learning for robotics. Okay, so they will both be handling the questions for us today. With that said, let me introduce our speaker for today. Pulkit Agrawal is an assistant professor at MIT. He directs the Improbable AI lab at MIT, and I'm pretty sure there is both a pun hidden there and a challenge hidden there, as he will tell us more. His research interests span robotics, deep learning, computer vision, and reinforcement learning. One of my favorite papers of his is this one called Learning to See by Moving, where they said things like, you can use your proprioceptive signals to understand how the features of the environment are changing, and that allows you to understand whether you are learning new things or not. It also evolved later into a broad line of work that many of us know by the name of curiosity. He has been very prolific and famous for some of his papers on these areas. Most notably, he got the Best Paper Award at Coral in 2021. He's the recipient of the Sony Faculty Research Award, the Salesforce Research Award, the Amazon Research Award, a Fulbright Fellowship, etc. Before joining MIT, he co-founded a startup called Safely You Inc. And he received his PhD from UC Berkeley, where he was advised by Jitendra Malik, who we had visiting just a few weeks ago. So Pulkit, very happy to have you here. Please begin.
Thank you so much for having me, and thank you for the generous introduction. So it seems like I couldn't get my clicker to work, so I'll be stranded in this corner. But hopefully, that should not prevent us from having a fun presentation. So, please feel free to pause me if you have any questions. We can make this interactive. So I'm going to talk about, the fun that we have been having with robots in the past few years. So if we look at, robots today, there are many impressive systems out there. So I'm showing you a video from Boston Dynamics Spot robot. And many of you probably, also saw this robot doing backflips. It looks amazing. So I think we have definitely made a lot of progress. And now very recently, so Google was leveraging these large language models to do something much more cognitive. So in the previous two demos, there were really physical tasks that the robots were doing. So over here, the prompt is, I spilled my Coke on the table. How would you throw it away and bring me something to help clean? And then the robot is saying, I would, find a Coke can. So it, finds the Coke can, it grabs the Coke can, and then it says that I'm going to, throw this Coke can away in the trash can, but it cannot throw the can, right? Then it's like, okay, to clean, I'm going to find a sponge. So it finds a sponge, picks it up, but then it cannot, clean with the sponge, right? So in some ways, this robot is able to figure out things like the Coke can must go into a trash can. To clean the mess, I should use a sponge. It's able to do this high-level reasoning, but is unable to execute these low-level skills required to actuate its high-level reasoning.
You say it doesn't refer to the can, it refers to the Coke. So it's just a wrong statement.
Yeah, so yes, I mean, there are definitely issues with how we provide tasks to the robot, right? And it has to, figure out like, Coke versus, the can of the Coke. And there's some ambiguity built into it. Now, this specific system, which I'm demonstrating, they had hard coded some of these things. So therefore, it was able to make these interpretations accurately. Otherwise, there would be a challenge, as you're rightly pointing out. Right? So, but the bigger picture over there being that even if we could do this reasoning, the low level still remains hard. Now, this video probably many of you already saw, and which is about just showing the hardness of the low level skills at doing basic things like opening doors, climbing stairs, so on and so forth. And this is not a new observation in AI. People for a long time have known that, for example, put by Hans Moravec, he said that reasoning requires very little computation, but sensory motor skill requires a lot of compute. Right. The point being that things that we thought were hard, like games like chess or doing language reasoning, actually don't require as much computation as do sensory motor skills require. Put by another scientist, Steven Pinker, he says the main lesson of 35 years of AI research is that hard problems are easy and the easy problems are hard. Right? And these statements were made in late 1980s, and they were known as the Moravec's paradox. Right? And turns out that even now, it's 2023, almost 35 years since these statements were made, and the problem still holds true. Right? So what does this mean? If I want, my robot to make me dinner. Now, what this means is that if I have to, do this, first I need to understand what is dinner, what humans eat, what the recipes are, what the cooking steps are. Right? Now, in the recent, past few months, with programs like ChatGPT, there has been a lot of success in, understanding these kind of things. But then the next question is, suppose I got a sequence of steps. Then I need to execute them. For example, if the sequence is get me the vegetable from the refrigerator and chop the vegetable, then we still need to do it. And this is, what has remained quite challenging. And this is what I'm going to be discussing mostly in this talk is, how do we make progress on this aspect? So, before even saying how do we make progress, let's review very briefly how do we do things today. Right? So the general, pipeline looks like this. Suppose I have a task where I'm trying to reorient an object in my hand, right? So I should not pick up the mouse. I pick up my clicker. I'm trying to move it in my hand. So I have a state ST and a goal state SG. And typically one has a model. What is a model? It tells me given a state and the action, what happens next. What we're interested in is using this model to find actions. Now, the trouble is that typically this model is quite complex. And therefore, inferring these actions in real time, which is necessary for adapting, is impossible. Right? Now, to see some examples, so for example, if I want to spin a pen in my hand, now for these motions, what is happening is the object is, and the robotic hand is making and breaking contact with the object. And then it also has to figure out how much force is being applied, which makes it an instance of a continuous discrete optimization problem, which we know is NP hard. Right? Similarly, if we look at a different domain, for example, we want our quadrupeds or legged robots to be in the wild and run fast. There are different complexities that we have to take care of. For example, the friction might be variable. The softness of the terrain might be variable. The geometry of the terrain might be uneven. It might not be flat. It might be sloped. And then if we're trying to run fast, we might hit actuator limits. We might have to execute high forces, which might actually damage the hardware. And then, the robot may not always be in control of itself because it might be in a flight phase, right? So all of these things add to model complexity. And the reason I am mentioning, about this model complexity is because that means that my process of finding actions to these models becomes quite slow, to the point it becomes infeasible to do real-time control. So the common practice in this scenario is for a human to go on and construct a simple model. Now, what I mean by a simple model is something that we can optimize in real time so that our robots can actually function. So what kind of, what do I concretely mean by simplicity, right? So if we look in the case of in-hand reorientation, we might assume that we're only going to manipulate objects with simple shapes, for example, convex shapes. Or we might assume that the object is in a way so that it is on top of the hand. So if the object is on top of the hand, then I never need to fight gravity. But if the hand is facing downwards, then I need to manipulate the object while fighting gravity. And other things might be that if we are working with complex objects, maybe we reduce the rotation range, right? That I only want to rotate objects by small amounts, or we restrict the finger motion itself, right? So, and if we make some of these simplifications, we can, solve these problems. Right? Similarly, if we look at locomotion, for different things which are complex, we can try to tackle them one at a time by simplifying them. And different works have done an excellent job of looking at these and finding simplified models. Right? Now, while this is great and has led to success, the problem is that this process is very tedious, right? So in some ways, simplified models allow us to make real-time inference, but they are very specific to the particular task for which they were constructed. They are human interpretable, which is great. But for every task, a human needs to go in and come up with a new simplified model. Is everyone with me so far? Okay, great. So, and then, the next thing, which I haven't really talked about, is that even to get these states, right, on which my controller is running, for example, the pose of the object, we are going to get it from perception, right? Now, often in these problems, perception comes as an afterthought, right? But what that means is, first you figure out how to solve the control problem and then say, hey, there are some variables that I need to infer. So now let me go and build a perception system which can infer these variables. Now, because of this, what happens is that if my perception system is imprecise and it has errors, the control system is also going to, the errors are going to accumulate because now I'm going to do planning with an erroneous state estimate. Right? So the reason, in my view, why physical intelligence remains a challenge is that if I want to acquire new skills, it takes a lot of time for a human to build a simplified model. And these simplified models only work in a very limited domain. And if I have many, many things that I want my robot to perform, the scaling law is not there. And the second challenge is that if we're doing it with perception, if perception is an afterthought, that leads to errors propagating in my control pipeline and eventually the system failing. So what I'm going to discuss is an alternative to the paradigm of coming up with simplified models. And the idea is we want to make coming up with simplified models easy to scale, right? Now, so instead of a human coming up with simplified models, if we can automate this process, right, then things can be on the right scaling law, and we might be able to learn many, many different skills. So what we're going to do is we're still going to be using the model that is provided, but now learn a simplified model automatically, and I'm going to call this a policy. Now, what do I mean by a policy? What I mean is I use my model, and given a task specification, we're going to roll out some data from this model. Suppose I roll out a trajectory T1, and this trajectory has some reward. So similarly, I can roll out many trajectories and record the rewards associated with them. Now we can condense these trajectories into a policy. A policy is something which will take the current state and the goal and output an action. And this policy has been found by maximizing the sum of rewards. That is, produce me trajectories which lead to high rewards. Right? So what you can think of is that this policy is doing nothing but amortizing the cost of optimization. Right? So instead of saying that I'm going to optimize the full model in real time or a deployment, we're going to have a separate training phase where we collect lots of data and distill that into a policy. And when I'm executing a policy, all what I'm doing is performing amortized inference. Right? So, so the reason the policy learning is easier to scale is because now I just need to provide the task specification, and then I can collect data to find a simplified model which is going to work for that particular task. Yes. Okay, great. So I'm saying the equivalent of a simplified model. Maybe I should correct myself. So on the left, once we have a simple model, the reason we construct a simple model is so that we can do inference at real time, right? So, but the problem is that a human needs to come in and simplify from a complex model. So if I want to perform fast inference in real time, is there an alternative? And the policy is an alternative of doing fast inference in real time. So it's not a model, but it is achieving the same effect as what a simplified model would achieve, which is real-time inference. Right? Yes. Yeah. So when I'm saying complexity, I'm looking at how quickly can I optimize through that model to find actions. So if that optimization or number of flops required, number of flops or the number of computations required to find the sequence of actions. So that is what my notion of complexity is. If you require lots of flops to find a sequence of actions, then that model is complex. If I require few flops, then that model is simple. So that's the notion that we're going over here. So now once we have a policy, right, the policy can perform real-time inference. It is also going to be specific to the tasks for which we train the policy, and it is going to be a black box, right? So we are going to lose something, which if we constructed the simple model, we would have. Right? But the good part is going to be that now I can scale. If this pipeline works, I can go to new tasks and scale it up. So this is what we are going to investigate, that does this paradigm actually work and provides us a way to learn many, many different things, right? And we're going to do this from raw sensory data. So we don't have this problem of first solving the controller and then having perception as an afterthought. Now, to build upon this, let's take a case study. The first case study I'm going to look at is object reorientation, right? And why look at this problem? For example, if I want humans, or suppose if I want robots to use tools, for example, take a knife and chop carrots. Now, what I need to do is, given a knife, I first have to grasp it. Once I've grabbed it, I need to ensure that the sharp face of the knife faces the carrot, because that is the only way I can cut the carrot. Now, in robotics, or this is something that humans do all the time. For example, picking up a screwdriver, reorienting it so that I can put in the screw. So now in robotics, we have had a lot of progress on this problem of grasping. But on the problem of reorientation, it has, we still, have challenges over here, right? So as I discussed previously, if you look at what has happened in reorientation is we have only built systems which work with few objects. Therefore, they do not end up generalizing. And, in many times in simplified setups, right? For example, the upward facing hand example I gave earlier, right? So what we set out to do was to say, could we build a reorientation system which overcomes these limitations? That it can work for a large range of objects, it can work for any hand orientation, and it is also going to work from real world observations. Now, what do I mean by real world observations? Are things that I can capture with commodity sensors such as a depth camera. So to give you a sense of this real world observation aspect, so when OpenAI, they had an in-hand reorientation system, this is how the rig looked like, right? So if you look at this rig, there are so many cameras around the hand. Why is that? Because they wanted to measure the state of the system very accurately. For example, the fingertip position, the object pose, so on and so forth. While this rig worked, but this is not feasible, right? I cannot deploy this system. So what we would like to have is something much simpler. For example, a hand over here reorienting an object, but maybe only one camera looking at it, right? Why a choice of one camera? Because if I want to put the system on a mobile manipulator, I can't put cameras all around, right? And therefore, we would want to work with something which is in some ways real world ready. So this effort was led by Tao Chen. And the paradigm we're going to follow is to train in simulation, which is the process of collecting lots of data, distill it into a policy, and then transfer this policy into the real world. Now, getting into the details of how it might work, right? So suppose there's a goal pose in which I want my object to go into, and this is a current configuration. So, and given the current configuration and some other variables, they're going to learn this policy pi theta. And what does this state consist of? I can have joint positions, the current pose of the object, the goal pose of the object, and some other things. And my action space is going to be change in joint position of the robotic hand. So I can get the desired joint position by the formula on the screen. And then we're going to provide some rewards. And these rewards are going to be how close do I get to the goal pose. And then we're going to consider many, many objects. And we're going to train a single policy which tries to reorient all of these objects. Is everyone with me on the problem setup over here? Just for the you mean as an input? Yes, for now, yes. So we'll come back to how to overcome that. Right. Okay. And we're going to use a standard off-the-shelf reinforcement learning algorithm, PPO, over here to find this policy. Right. So now what I've done in this slide is I've written down many different things that go as input into the policy pi. Now I'm going to call many of these variables as privileged information. Why is it privileged? Because things like object pose, I cannot measure directly in the real world because they're simply not available, right? But in simulation, I can measure them easily because they are available, right? So things that I can measure in simulation, but not in the real world, are things which I'm calling privileged. Now what they do is they make the learning process be easier. So they can help me find a policy easily or quickly learn the policy. So let's first see how this system works, right? So I'm showing some results of this policy as this hand is trying to reorient this object to the goal pose shown on the left, right? And we're going to test this hand on objects that it has never seen before, right? Here are some more examples of objects that the hand never saw before. And what you can see is it is able to perform this reorientation task. And it also generalizes to many different and complex shapes. Yes. No, there is not. So which was a surprising point to us, that no object shape information is used in any of these policies. And still they're able to reorient a diverse set of objects. This is not to say that if we had object shape, maybe the performances might improve even more. But we can get reasonable performance without any object shape. Yes. So there's no camera right now. It is just the variables that I described over here. So joint positions, fingertip velocities, joint velocities, so on. It does not know. It does not know those things, right? I mean, it could, infer it somehow, but there's no explicit knowledge that we are providing it. Yes. So in this particular case, we were seeing, errors which were less than, 6 degrees, right, in the full SO3 space. And what we found is, around 75% of the times you could reach within 6 degrees. So that is what I mean by, good reorientation over here. Yes.
Contact dynamics are the surface all the same.
So there is different properties, like friction of the surfaces is varied, right? I mean, we do use convex decomposition in simulation. And how good the contact dynamics are, I think the real proxy is how good are the real world results. So let me talk about the real world results, and that will be a measure of how good the dynamics, the simulation dynamics are. Right. So okay, this thing works in simulation, but we all know simulations are approximate in many, many ways. So the real question is, will this actually work in the real world? So to test this, we didn't have the shadow hand, which is very expensive. And also what I hear is it breaks a lot. So what we have is this, another hand, which is, built of open source components. You can build it under $2,000, right? It has 4 fingers, and it is reorienting these objects in simulation. And then, what we're going to do is we're going to observe the point cloud from the camera and get the joint positions of this robotic hand, feed it as input to a controller, which is going to be a policy, and it's going to tell me the joint commands. So that's pretty much the inputs and the outputs. And what we had previously was this policy trained from privileged state. So what we found is that this is easy to train, but this is something which we cannot really deploy. So what we have in the real world is this, the point cloud that I'm observing, and the joint positions. So somehow, these things need to be inferred, right? And the precise inference is hard. And this is why previous systems had to use a big camera rig to make accurate predictions. So instead of trying to predict these inputs to the policy, we're going to look at a different way of solving the problem. Right? The different way is going to be that let's take whatever we have as input, right, and try to directly train a policy. The reason for this is because if there are errors which come in the perception stage, they can be compensated by the controller because they're going to learn the perception and the controller simultaneously. But the problem with following this approach is that we can deploy such a policy if we can train it, but this policy is very hard to train, so we cannot really train it. Is everyone with me? On way? Yes. Question. So yes, so the goal pose is a way of specifying the task. And what we do right now is that we take the object, orient to the goal pose, and measure its point cloud. And that's how we provide the goal pose. It's a point cloud in the goal orientation. Yes. 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 So if you have a single GPU, maybe in a couple of days, you can train the policy. It depends on how many objects you want to train on, how much randomization you want to perform on things like friction and so on and so forth. But single workstation, couple of days. Yeah. So all the experiments I'm going to show are going to be in a single workstation. Right. So now that we are stuck with this dilemma, what do we do? So the insight over here is that supervised learning is easier than reinforcement learning. Now, what do I mean by this? So if I'm trying to learn a policy directly from rewards, then I'm trying to figure out what the right actions are, and also trying to figure out how to estimate those actions from perception simultaneously. So there are two hard problems I'm trying to solve. Right? What if I can simplify this? Right? And the insight is that instead of doing RL, what if I used, or if I already knew what the right actions are, right? So this I can get because I can have the policy which is trained with privileged state, which is providing me what the right actions are, right? And then I can just train to predict these actions from the observations which are available in the real world. Right? So this is going to become essentially, doing supervised learning from perceptual data. Right? And this is why this problem is going to become now much simpler to solve than the original RL problem. Yes. So in simulator, we can run both of these policies simultaneously, right? So in simulator, I know all these variables, which is the privileged states. I can predict the action. Now I also have the point cloud corresponding to the same set of variables. Right? So this is only possible in simulation to do. Right? So therefore, I'm running both the policies on the same state of the simulator. It's just that the observations of both the policies are different. Yes. For computational reasons is one thing. I mean, rendering is very slow, but also if your state space is large, then learning policies also takes a long amount of time. So I'm going to come to it. I'm going to come to it. Oh, so the compute, okay, so what it absolves you is that in the first case, you were trying to figure out the right actions and trying to learn how to predict those actions simultaneously. So now I don't need to figure out what the right actions are, because my first policy is giving me the right actions. So my exploration problem has essentially reduced because I don't need to explore anymore, which is what makes the problem easier. It does not work, right? I mean, and so there are two reasons why it does not work, right? One, you can say, is the speed of rendering. Now, suppose you somehow made rendering be very quick. Even then, it becomes very hard to learn. Right? Now, that is an empirical observation. And the intuition behind is that you're trying to solve two things simultaneously, trying to figure out what the right actions are, and also trying to figure out how to predict those actions. Now, it could be possible that in future, there are better RL algorithms which can learn directly from point clouds, but today's algorithms are simply not good enough. Yeah. Yes. So there's no claim about optimality. Yes. Yes. Yeah. 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 So yeah, just to answer the question, yes, we are not. We want something. We want a solution which can reorient my objects, but we're not claiming it's the optimal solution. Okay. Any other questions? No? Okay. So now we're going to train this policy using supervised learning, and people who are familiar with this would know this as behavior cloning or Dagger. That's what we're going to do to learn the policy. Now, turns out, and what we're going to call the first one is a teacher policy because it is providing me the supervision. And the second policy is what we're going to call the student policy, which is learning from the teacher. Now, it turns out that even doing the supervised learning is infeasible in just terms of the amount of time it takes. And the reason is something which was brought up before, that rendering point clouds is still very expensive. But if you're in simulation, we can always play God, right? So what we can do is, right, instead of rendering the point clouds, what we can do is first, I have a teacher policy which I train. Then I train the first student policy, which takes the CAD models and just samples points on them to get a sampled point cloud. So it is still a point cloud, but it's going to have no occlusions or no missing information, right? But this is very quick to generate in simulation, so we can train with that, right? And then to tackle the real world statistics, which are going to come from occluded point clouds, we can fine tune this policy a little bit using rendered point clouds. And by doing this, this process becomes much more feasible to do, right? And that's why we need to do this two-stage, student-teacher learning to get the policy. Yes. The original teacher policy still. Yeah. We just use the weights of the student one and then fine-tune the weights. Okay, so now let's take this policy and let's look at how it performs, in the real world. And just to mention that this idea of teacher-student learning has been explored in different works in different ways. Right? So just to make everyone be aware of the setup once again, right? I'm just showing the front view and the side view of the setup. And I'm going to show you evaluation on novel objects that the policy was not trained on. So this is the first example where the goal orientation is shown on the top right. And let's see what the system does. Here's another example where we're going to hand the object and it's going to orient it to the goal pose. Now it not only can orient it to the goal pose, but also stop there. Right? Turns out that continuous reorientation is easy, but if you have to go to the goal post, stop, and then again start, that ends up being much harder to do because you have to fight inertia. Now, by no means the system is perfect, right? It also has failure modes. So right now, in 50% of the episodes, we end up succeeding. But like what then? Oh, yeah. So over here, when so in simulation, when we were computing everything, it was around 6 degrees. In the real world, I think when we are computing success, is around 20 degrees. Yeah. So I mean, getting precise orientation is still challenging, and I'm going to come to some of the reasons behind it, right? Now, here is another example where we are showing that after reorientation, we can move the arm around just to show that these graphs are stable, and then we can actually perform things like picking up an object, reorienting, and then thinking about placing them or using tools in the future, right? So, what are the takeaways? Right, the takeaways is that by using simulation, we can learn policies which are able to perform a contact-rich task, right? And the key ideas were to to make use of privileged information in form of student-teacher learning. We had to do a couple of things to speed, point cloud training, which took it from 20 days to 4 days. Then there were architectural choices which had to be made so that these architectures can work in real time. So we're working at 12 hertz using sparse CNNs. Then there's a part which I did not mention, but this is needed to get good performance, is that we need to match the simulator to the real world. But when I'm matching, I just mean matching the hand, because hand has a couple of things like the motor dynamics, the lag, which are not well modeled in simulation. So what we do is we do some system identification of these properties. And then there is a dirty laundry list of needing to design the reward function and some hardware considerations. Any questions? Or yes.
Yeah, follow-up question. Yes, question.
Mhm.
So it seems that objects here they are all 3D, and it does seem that there is an assumed object distribution there because they all fall under a certain size. So do you have a more explicit statement of what the assumption of the distribution of the object is?
Yes, so we can work with non-3D printed objects, right? And we can also go to textured objects. It does not matter because we don't use RGB, we only use depth. The assumption is the object needs to fit in the hand. If things are too small, they wouldn't fit in this hand. If things are too big, they wouldn't fit. But so if it becomes physically infeasible for the motors to actuate that much forces, then it is going to fall down. But apart from that, we're not really making any assumption about the object shape. Now you might say, hey, all of these objects, maybe the friction is in a particular range. What happens if I take a ball, put it in oil, and give it to the hand? Right? In that case, it will be more challenging than what it is now. Right? And a part of those reasons is why we are not getting even more accurate is because this is purely based on vision. There is no tactile feedback at all in this system, right? So I think once we start integrating tactile feedback, we can really try to be more precise and also detect when the object is slipping out of my hand, something which we can't do right now. Yes. I don't know. Yes, almost, yeah, all the objects that we experimented with are rigid. Yes.
So you said that how should we evaluate?
Great. Excellent question. I think the eventual success is going to be if I can start using tools successfully, right? For example, if I can take a screwdriver and screw in a nut, that is the eventual success that one should evaluate on. I think this is an intermediate step. And the only claim that we are making is that previous systems which were solving this problem made some assumptions, for example, only working with simple geometries. If they work with complex geometries, they're not doing the full SO3 reorientation, or requiring a lot of other sensory operators that we cannot generalize. So the point is this method, now that we can solve this problem, we can apply the same method to different problems and scale it up. So this is just showing that there is a set of things if we do, there is a path to scale for now. That's the takeaway. Yes. 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 So we don't do system identification for the objects, just for the hand. Just for the hand. Because we cannot really do it for objects if we want objects. I guess one could do it, but then you need to have a model a priori to identify those parameters. Yes. So you could take objects with different materials that we can do. You can take objects with different materials. That should be fine. Yes. Yes, Michael.
All right.
Yes. Yes.
Still just kind of, you know.
Excellent question. So there are, two parts to the answer. The one part is the policy with the point clouds is forced to mimic the policy without the point cloud as input. So it has no incentive of doing it. Now that is something we are working on right now to overcome that limitation, but right now there is no incentive. The second part being you can do some evaluation where you provide different shaped objects and try to study if it is doing the same motion every time irrespective of the geometry. That's not the case. So it is adapting, and the reason it can adapt is probably because it is a sequential model now. So it does know that if I apply forces on the previous time iteration, if my fingers did not move, I hit something. To the extent that is useful to mimic the teacher, it is using the shape. But it cannot use the shape and become better than the teacher, is what you would ideally hope for. And that is something which hopefully we'll get to in some time. This question in the back, same. Great. Yes. Yes, I think, in theory, if we do simulation with those distributions, it should also work fine. Now, we haven't done experiments with it to show that yet. Yes.
You're only using the distribution, and you're not using that confirmation towards information. So I think making the count down is kind of taking advantage of the gravity, and we try to really hard.
Yeah, I mean, gravity is a two-edged sword, right? I mean, gravity, you have to fight gravity because if you make an imprecise action, the object might also fall down. But over here, we are able to convert it into something that we can use. Now, in these experiments, we haven't done, on over, but I think in a previous paper, only in simulation, we did with the object being on the top, it works fine. Yeah. Let me, oops. Okay. So, okay, so it works, but there are also problems. And the reason the problems are that, first of all, this hand has no touch sensing, right? So what we are doing now is, we presented this touch simulator where now we can start, simulating touch readings, right? And what we can do is we can put touch sensors in complex geometries, right? So all the white dots that you see are touch sensors that we can put so that we can start, incorporating touch signals into our pipeline. Right? And what we have demonstrated is a very simple task over here where we trained policies to do peg in the hole task, right? We have to insert this, cuboid inside this hole. We train in simulation and deploy in the real world. Right? So now that we can get some handle of learning from tactile sensing, we can start looking at where we want to improve the reorientation by using touch sensing. So what you see is this hand whose fingertips have touch sensors, specifically gel side sensors are attached over there, but also other problems, which are like, if I put my hand in a bag, can I explore and find an object of interest? So here is a simplified version of that problem, right? So where we have this hand touch an object. So it touches this object to form a representation of this object, right? And after it has done this, what we do is we throw in other objects, shut off the lights, and let the hand explore. This is similar to you waking up in the morning, right, and trying to find your mobile phone, right? So it goes around the table trying to find, where the objects might be. But once we are trying to sense with touch, we have to be careful because to sense, we have to apply a force, so we can record the touch sensing. But if we apply the force, the objects can also move. So you have to balance these two criteria, right? Now, once the hand has touched all of these objects, then it's going to match them with the target object and finally pick up the one which is the closest to the target. Right? Now, I think this whole idea of acquiring information for perception is an old one and has been widely studied. I think what we're just demonstrating is that touch sensors are now ready to the point that we can start using them, and we have tools in simulation that we can also start using to start attacking more contact-rich problems. Yes. So that is something we haven't gotten to yet, because when we started doing that, we realized, hey, there's no good touch simulators. But then the first thing was to build a touch simulator. Then it's like, what are the touch sensors we can start using? So this is our first foray in trying to figure out, can we even use touch sensors, right? So next would be to put it together, but it's not done yet, right? When this work, yeah, okay. Right, so next, okay, so we could do things, okay, so we have some handle on touch sensing, but the next question becomes is, this hand is actually quite different, right, than a hand which a human has. It has no palm, the fingers have no compliant, they're rigid. So almost what you see in the videos is manipulating objects with chopsticks, because everything is so rigid over here. And then how do we know, is this finger shape optimal or not? And so what we have started doing was to build a pipeline where we can optimize for hand designs, right? So what I'm showing you is, 4 different hand designs optimized for 4 different tasks. And these hands are all 3D printed. And the blue thing that you see are actually touch sensors. So they are kind of gloves that one can print and then put on the fingers itself. And this pipeline is automated because we have a grammar to generate hand designs, right? And this is just showing this process of sampling from the grammar where we, get a different, a particular design. Now, if we use, some predefined components, the shape of those predefined components may not be ideal. So a user can go in and deform these shapes. Okay, yes, it showed the process. Right. So you can deform the shape, but what we guarantee is any shape deformation you do, it's going to be 3D printed. Then what we can do is we can go specify where you want touch sensors to be. Right. So there's a process where we click on the parts where we want touch sensors to be. And then these files, both the gripper file and the touch sensor, they go into a 3D printer so that we can print both the touch sensors and the hand, assemble them together and, start doing some tasks. For example, over here, this scissor is trying to cut this piece of paper, and you see how the touch readings go on your left. Right. Okay, so I'm going to skip some of these, more demonstrations of the hand. And, then, of course, we can co-optimize both the design, along with the control. And I'm showing you some more examples of designing, custom grippers for the tasks that we're interested in. Right. And this was work done a lot in collaboration with Wojciech, who really specializes in 3D printing and touch sensing. So what we have now is like this pipeline where the controller, perception, and hardware all kind of speak the same language. And therefore, we can scale all of these 3 things simultaneously and also co-optimize them. Now, in interest of time, I'm going to briefly describe a second case study, and then I'll stop. Right, and this study is in rapid locomotion. And the context for this study is that we're still going to use the same framework, but just to showcase that we can go to a different problem setup. Right, and this work was led by Gabe. And the context is that we have robots or quadrupeds which can walk very diverse terrains, but they're slow and conservative. On the other hand, we have these systems which can run faster than Usain Bolt, but in lab environments, right? On a treadmill, externally powered, with some external support, so on and so forth. So what we set forth for ourselves is, could we get something which is more similar to fast locomotion in the wild? So again, we're going to follow the same philosophy of training and simulation and then deploying policies in the real world. So here are some results of, first this, mini cheetah or the quadruped we had, it broke the speed record, which was previously held by the same robot, right? But now the cool part is we can take the system outdoors. For example, over here, it's spinning on ice. Or we can take it, on gravelly hills. So on the left, we are showing the baseline controller, which the robot shipped with, which at some point, struggles to move on the gravelly hill. But our controller, although the way it walks is not elegant, it ends up making progress and, goes on top of the hill and is able to deal with, things like stones, like this small gravel, which we can't really simulate. Right? Here's another example, comparing with the baseline controller and the more robust controller. And we were, taking this robot out, and one day what happened is a screw in a motor came out. So what you see is that this robot will limp, but it's still walking, right? And this is the kind of robustness we were hoping to achieve or to test for. Right? Now that we can do agile, locomotion in the wild and do dexterous manipulation, right? We can kind of combine them, where we are doing all those three things simultaneously. And this is well illustrated by, soccer. So here is again these systems, trained in simulation. Right, but now, for a slightly different task of playing with the soccer ball, right? And even if they fall down, right, they can get themselves up, keep moving. And maybe again illustrating the kind of robustness we can get. Right? So all the tasks that I've shown you until now, right, they all use the same code base, right? It's the same simulator. All that we are changing is the task specification. Right? So in some ways, right, so what I presented you are, a framework or a way of thinking about, using models to learn policies, which can help us, tackle contact-rich problems. And the good thing is that we can scale it up now by changing the tasks that we want to do. Now, there is some success, but there are tons of open questions also, right? So with that, I'm going to stop, and I'm happy to talk about the open questions or other questions you might have.
Questions? Okay. Yeah, thanks for the great talk. Really impressive, like hardware demonstrations. One thing I have a question on is just like your view on simulators in general. It seems like having a good simulator for all of these tasks really was like a key component to like, overcome the RL sample inefficiency. Do you think that you can just keep on pushing this into more complex tasks where simulators might be more hard to like engineer? Or is there some way to like adapt your systems to data collected like at real time? Like just in general, what are your thoughts on simulators and its importance?
Yeah, excellent question. So I think maybe there are 3 points to be made. I think first is that we don't necessarily require accurate simulators, right? And the reason I'm saying this is, for example, gravel is something that we cannot simulate. And you might ask, why is it that we're going up on gravel while we can't simulate it? The answer is, think about what happens when you go up on gravel, right? The gravel shifts down and it is slippery. So if you are on, even on flat ground, if I simulate, if I make it very slippery and I randomize the forces that are being applied on the robot, then I get the same effect as I would get on a gravel. So if the assumption is that the space of reactions that the robot needs to learn is much smaller than the space of all environmental variation. If that is true, we will be able to go to more domains which are not emulated in the simulator itself. The second point you mentioned is, what happens if we don't have a phenomena that is modeled? For example, in the soccer playing, the ball has drag. If you have a ball going on pavement, it just rolls. If you take the ball on grass, it's going to stop. But this rolling, friction or this drag was not there in the simulator. So we can augment simulators with learned models or just specified models about phenomena which are not there. The third question you might ask is, what about tasks which we can never or will be very hard to simulate, like working with liquids or deformable objects? What do we do over there? I think the hope over there is that even if we can go and solve many rigid manipulation tasks, we would have learned some useful priors of how to just do general manipulation, move my hands, hold objects, that the deformable stuff we can learn with few interactions. So that's the hope. So think of this as pre-training, and we will pre-train on as many tasks that we can pre-train on, and then hope that for the tasks that we cannot simulate, we can do some few short learning on them.
Thank you for the very interesting talk. So I have a question about, it's more of a high level question. So for all these tasks where it requires a lot of dexterity, do you think the limit right now is more on the software or on the hardware? So the thing is, yes, we have all these amazing AI driven software coming up, but the thing is the motors are still from, they are pretty much the same. And we're piling motors on motors to make the hardware more complex, and the sensors, they're moving forward, but also rather slow. So where do you think the bottleneck is to achieve really the kind of dexterity that our hands have?
So I think there are challenges both in software and hardware right now, right? I mean, the approach that I described of doing teacher-student learning, like Michael's question, for example, right, that the student is trying to mimic the teacher precisely, so it can never use perception more efficiently. I mean, those kind of questions are still open. We still need to design reward functions, which is tedious, and we would like to go in a world where designing reward functions is much easier. But I think good hardware is also going to be important. I think what I think about is, measuring forces over here and having some kind of compliance, which are the two things that we don't have. And maybe third is the size, because the fingers are too big, and the human environment is built around the human hand. So all objects are, similarly sized to a human hand. Now, if you start making things be small, right, then, if you make your hands be small, you require smaller motors, and therefore they cannot give you so much power. But again, I think this is where the drone revolution has really been good, because now we have these high torque, but small motors. So I think the hardware has also progressed. So I think we can now, at this point, start rethinking even the hardware, because what people did was initially you needed to have big motors. If you didn't have big motors, you would do hydraulics or tendon-driven control, because the motors which were small would be high speed but low torque. But I think now that is changing, which will enable a new phase of hardware design.
Any more questions? Okay, I have a question then. So I was wondering to get your thoughts on what are hard tasks in robotics. So before this year and the last year, to me, dexterous manipulation is really hard, but there are many works coming from your group and other groups that have shown you really don't need high bandwidth perception. For example, you can just do in-hand orientation using, not even using vision recent, right? So there's been a trend where tasks that I used to consider to be difficult are now easy, and that trend has been going. So what are some of the remaining hard tasks in robotics?
So I would say don't let the results fool you, right? I think it's definitely progress. right? But if I have a 20-degree error, I cannot use a screwdriver, right? And the things that you are, and that is where maybe we do require, precise, feedback. Or for example, how do we use touch sensing, right? And if I don't have perception coming at high frequency, I may not be able to perform those tasks. So, I mean, to me, it seems like the next big push in dexterous manipulation will come from doing more work on sensing and hardware than the algorithms per se. And maybe to get to the point of where I can take a screwdriver, pick it up in my hand, and even rotate it in a nut. But at that point, we're going to, maybe I don't know what will happen beyond it, right? Maybe the same algorithms will work. Or I think what will really happen is this is designing reward functions for every task will become tedious. And then probably we'll have to fix that. So in the short term, I think it's maybe my bet would be more sensing and hardware. But in the longer term, I think it probably will come down to all three again.
Hi, Pulkit. Thanks for the great talk. And my question is about the imitation learning part of what you presented. So as you mentioned, and also there's a lot of evidence in like robot learning community nowadays. Learning from demonstration is quite effective in many tasks. And I was just wondering for the specific task of dexterous manipulation, but humans can have tactile sensors on them and provide quite a lot of demonstrations. There are also a lot of like video data sets of human hands doing things. Like, what are your thoughts on learning from these sort of demonstrations for robot dexterous manipulation?
So my thought is that, a lot of these video data sets provide us what tools to use, where to touch them. So they're excellent priors about what to do and how to manipulate. But how to act, what commands to give to my robot fingers, I think those things are very hard to get from the data set. So what you can think is now once we have the basic skill of how I can reorient or pick up objects, then that enables me to interpret videos in a more useful way. Because now my videos can give me sub goals essentially. For example, in what orientation should I orient the object, or what should be the goal of my reorientation system? So I can look at videos, get those goals, and then deploy these low-level skills. Collecting data with tactile sensors with humans. And I think the problem will be scaling it up. So video is a good thing is everyone can record a video, but not everyone can record tactile data, right? I mean, even if you build your glove and ship it, how many gloves would you ship? So I would first still try to see what we can do with tactile simulators. Yeah.
Are there any more questions?
Yeah. Thank you. Let's thank the speaker again. Thank you for the very engaging talk, and number of questions demonstrates how much they like it, how much they're interested in it. A few closing remarks. Please tune in next Friday, same time, same place, for the next talk by Professor Nancy Amato from the University of Illinois in Urbana-Champaign. Thank you so much.